Hello everyone. Welcome to Team 13's presentation of the project for ME555 Design Optimization. Our team members include Guruprasad Srikrishnan, Raghav Tripathi, Saransh Goel, Keshav Kulwal, Vishal Salvamani, and Dev Kahodaria. In this project, we have decided to analyze and subsequently optimize the design of an automotive braking system. The primary system we have chosen for this project is the basic automotive braking system as shown on the screen. Its major functional parts include brake calipers, pads, rotors, and the master cylinder. The rationale for the system level optimization problem was that these subsystems represent the key mechanical, electronic, and hydraulic components that collectively determine braking efficiency. Optimizing them individually while considering their interactions ensures a well balanced and high performance braking system. As you can see on the screen, here are the main inputs and outputs of three subsystems previously described. The outputs are fluid pressure for the first subsystem, the frequency of the ABS, the force on the calipers for the second subsystem, and finally the brake clamping force for the third subsystem. Further, you can also view the system flow diagram on the right, where the dashed lines represent the system boundary, which indicates that the main output that we are finally focusing on is the braking efficiency. The shared variable is the brake swept area ABS between subsystems 2 and 3. The coupled output variable is the brake clamping force FBC from subsystem 3. Additionally, FCAL and FABS are the coupled outputs from subsystem 2. This can also be seen through the system boundary diagram.
Here is the optimization model that we are using for our first subsystem, the hydraulic system. The design variables include the master cylinder diameter and the stroke length. The constraints for the system are also shown. The diameter has an upper and lower bound of 38 and 19 meters, whereas the height is constrained within 150 and 100 mm respectively. The objective function here is to minimize the volume of the master cylinder. In this slide, we are showing the mathematical modeling used to optimize the objective function. Here the output fluid pressure has to be maximized. To optimize this, we have to minimize the volume of master cylinder while all other parameters remain constant. We have a few assumptions in our model, like we are assuming an ideal scenario where the force applied on the pedal by the driver is constant. The major steps incorporated in the modeling are shown in the bottom half of the screen. The algorithm that we have used for this optimization is the interior point algorithm, which is fairly quick and is good enough to find local convergence point. We have implemented this algorithm and code in MATLAB for various reasons as shown. This slide shows the optimization results after running the algorithm. As you can see from the table, we have received the same output for 5 different input values. This indicates that the algorithm used is deterministic in nature and converges to the same optimal value.
To discuss the results and major engineering interpretations, we have achieved the optimal values as 19 mm for master cylinder bore diameter and stroke length of 101.27 mm for the first subsystem. It is worth noting that we received the same optimal solution regardless of the initial input, which indicates a well-defined global optimum. Further, it was realized that we should not reduce the bore diameter below 19 mm, as that would be infeasible and result in an unsatisfactory design. Here is the optimization model that we are using for our second subsystem, the brake control unit. The design variable includes brake swept area A sub BS, the efficiency of venting pattern E sub VP, and the speed of wheel V sub W. We have a lower and upper bound on each design variable as the constraints. The objective function here is to minimize the sum of frequency of ABS, the force on caliper, and the brake temperature. In this slide, we are showing the mathematical model used to optimize the objective function. Here, the output forces and the temperature have to be minimized. To optimize this, we have to minimize all three objective functions so that the sum as a whole can be minimized. We are assuming an ideal scenario where the material as well as its properties does not degrade over the time and the hydraulic pressure from subsystem 1 remains constant. The steps incorporated in the modeling are shown in the bottom half of the screen.
Coming on to the optimization model for the second subsystem, the algorithm that we have used for this optimization is the interior point algorithm by utilizing the fmincon function, which is fairly quick and is good enough to find local convergence points. We have implemented this algorithm and code in MATLAB, which offers several advantages as shown. Talking about the optimization results, as can be seen from the table, we have received 5 outputs for 5 different input values. We got a consistent functional value of 100 for every run. This shows that the design variables play a vital role in producing an optimal output. The values are well within the error margins of each other and show very little discrepancy. The major results and engineering interpretations are as follows. We have achieved the optimal values for brake swept area as 2.95 square inches efficiency of venting patterns 16.9%, and speed as 50 rpm on average, accounting for minor discrepancies discussed earlier. Consistency in functional value indicates robustness in the system. Moreover, it is indicated that a smaller brake swept area, smoother venting, and lower wheel speed result in overall lower braking forces. Here is the optimization model that we are using for our third subsystem, rotors and pads. The design variables include rotor diameter, brake swept area, and the friction of the brake pad material. There is a lower and upper bound on each design variable, which are used as the constraints. The parameters taken into account for optimization for this subsystem, as well as the objective constraint trade-off, are displayed on the screen.
The objective function here is to maximize the brake clamping force, FBC, which is converted into a minimization problem with a negative sign using a null negative form. The intermediate constraints are shown on screen, while the objective constraint trade-offs indicate that there is a requirement of designing a rotor that is large but also light, while providing high friction between the assembly components. In this slide, the mathematical model is shown. The primary output is the brake clamping force, which needs to be maximized. To optimize this, we have to simply find the absolute highest possible value of FBC and multiply it by -1 to obtain a minimization problem. We are assuming an ideal scenario where the components remain in relative rigidity with respect to each other, and that the coefficient of friction does not change when the temperature changes during the rotor pad contact. The algorithm that we have used for this optimization is the genetic algorithm, which is effective in solving highly nonlinear functions while also providing global maxima and or minima, rather than just local solutions. We have implemented this algorithm and code in MATLAB for several reasons, as shown.
The table shows 5 outputs for 5 different input values. The values are well within the error margins of each other and show very little or no discrepancies. This may indicate that the genetic algorithm is finding slightly different local optimal values, but they all seem to be near the global optimal value. This could be accounted for by the different paths that the GA takes in each iteration. We have found the optimal values of radius being 0.5 meters, brake swept area of 0.01 square meters, and friction coefficient of 0.2. On average, taking into account that slight discrepancies provided by the multiple paths that the GA takes. Moreover, it is indicated that smaller brake swept area is required, which keeps the material usage at an optimum level by keeping a large enough surface to provide enough friction. This contributes to additional pad wear. To summarize everything, after following the optimization procedure for each subsystem, we have arrived at the following optimal values for different variables involved. We also have shown the corresponding optimal function value, which remains consistent across different runs. Thank you.